Okay. Well, good afternoon, everyone. I'm John Mann, Director of Education for Lakeside. And for today, we're fortunate to have Dr. Jay Leonardson joining us for 2 lectures today and tomorrow as part of our environmental lecture series. This lecture series focuses on our warming planet. And for today's session, focusing on the connection between warming and increased urban heat island effect and associated increases in primary and secondary pollutants. As a reminder, Jay will be back here tomorrow at 3:30 to examine the connection between climate change and our more frequent and severe wildfires and the implications for human and economic health. As always, I always ask you, please mute your cell phone ringers and help me in welcoming Jay Leonardson.
John, thank you very much. Thanks to the technical folks for getting this all set up. And big thank you to you folks here. Bless your, so I live in North Carolina now. And one of the expressions I needed to learn as soon as I got there, and now it's one of my favorites, bless your heart, right? Which covers a broad spectrum, right? Because you can kind of, it makes you sound kind of sweet, but at the same time, it's like, bless her heart, what was she thinking about with that outfit kind of thing, right? Right? So I love this expression. But yeah, so bless your hearts for coming. I mean, it's a gorgeous day out there, and you're inside listening to me yammer on, so I appreciate that. Yeah, so it's a small group, and I'm just delighted to have you folks here. Share a little bit about me to give you maybe context, and that might help you to understand some things related to the presentations. So I have lived all over the United States, was born in New England. I think the little piece in the paper said something about that because my mom is from New England, and that's where my dad from the Midwest married her when he was in the service. Yep, that's how that all worked. Spent my elementary and middle school years out in New England, moved up to New Hampshire for a little while, Massachusetts, and then Dad got transferred to Cleveland, Ohio. So I did my first 2 years of high school in Fairview Park, Ohio. So this is a homecoming of sorts. I've been back to Cleveland a couple of times, right? But, you know, being here on the shores of Lake Erie, right, and seeing all the glacial landscape, how flat everything is, it's an adjustment for me again, because in North Carolina, we got a bunch of mountains and there's vegetation everywhere. So, yeah, it's just a lot of nostalgia here for me. And when we walked through the gates yesterday of Lakeside, well, actually we got a ride through the gates of Lakeside, I really started to understand just how special this place is, right? My blood pressure, I think, dropped like, I don't know, 20 or 30 points, completely relaxed. And so I appreciate the audience today, and I appreciate your time. So maybe that's not a bad transition, right? Appreciation into my very first slide, right? I like to kind of start with this slide because when we're talking about, so I teach earth science. So I'm a meteorologist, but I teach in a geography department, so I'm a geographer as well, right? So when I'm talking about environmental sorts of issues, earth science issues of the world, I start with this slide because I think it gives us perspective just on how special our planet is and kind of what a poor job we are doing, and I know I'm preaching to the choir here, right? What a poor job we are doing at taking care of it, right? It's special because it's got more water, certainly, than in any other celestial bodies that we are aware of. Right? We used to think that we were the only ones in our solar system with water. We now know that there are other planets that at least did have water at a certain point in time, and maybe still do, right? But we got a lot more water, which we can see expressed as clouds, and of course the vast oceans right there. And I definitely prefer, right, that home to that one over there on the right, right? So when we, you know, as we're mucking our planet up, and I'm going to focus on how we're mucking up the atmosphere today, right? Let's just remember that the other options are not so great. Got a little, okay, I got to use my pointing. How is the volume, by the way? Are we good everywhere? Okay, hey, thank you. All right. So as I'm moving through the slides and chatting about the various topics, right, this is kind of the central theme. right? We've got a whole host of environmental issues, and climate change is only making things worse. Got a little thermometer over there, right? But that's just, one of the problems, the increasing heat. Okay. So kind of continuing on that theme, how special our planet is, right? There's really no place like home. Most of the attention these days, right, seems to be on, oops, there we go, can't operate this thing. That one right there. Seems to be on things like more severe weather, right? And particularly here, I mean, we're focused, that's a hurricane, a classic hurricane with a classic eye, right? So both more frequent severe weather events like hurricanes and also more severe events. I don't know, so I was taking a look. I've been following this a little bit lately as I've been traveling. I watch the Weather Channel in various hotel rooms, right? Don't get it at home because I don't want to pay for cable. But anyway, right, they've been talking about the tropical system hurricane that's moving through the Caribbean now. Beryl, I think is its name, right? And Beryl is the earliest Category 5 hurricane ever in the Atlantic, right? Normally this time of the year, the oceans are not warm enough and the atmosphere is not, conditions in the upper atmosphere are not suitable for Category 5 hurricanes, but yet we got one already, right? So just kind of a classic example of how storms are becoming more severe, right? And then of course, the slide over here is emphasizing the melting sea ice and melting glaciers, and we're most concerned with melting ice on Antarctica, right? Because that is the biggest ice sheet, right? And that's melting more quickly than the scientists even feared, right? And then, of course, over here, people are concerned with, habitat loss, right? And then I like to throw this slide in sometimes because, for the longest time, so I've been teaching at the University of North Carolina at Greensboro since 1997. Moved down from Milwaukee, and they wanted to hire me. I needed a job, so I went there, and I've been there ever since, right? And so, way back in 97, I was talking about climate change. So like the ostrich, right? We have had our head in the sand. We're maybe picking it up out of the sand here now, but not quickly enough to solve our problems, right? And just, some other themes here with climate change. So New York Times article during you probably noticed this during the recent Hajj to Mecca, right, in the Middle East. Over 1,300 people were killed because of the extreme heat. Temperatures around 125 degrees Fahrenheit, right? I mean, it's hot in that part of the world, but this is kind of even mind-boggling. And humid as well, yeah, which only compounds things. And we're going to chat about that in the context of air quality, how humidity can sometimes help air quality and sometimes hurt air quality. And then, the seasons are shifting, right? Spring is arriving earlier. Just a headline here from the New York Times. The dog days of summer are here early, but New York City is trying to adapt, right? So summer's arriving sooner and lasting longer. I think you folks, well, I know in the Midwest in general, I think it was last week sometime, some record-setting temperatures. I think here you might have had temperatures, right? Over maybe 100.
Our average is really good.
Okay. So, and we're going to talk about that's coming up next. All right. So with that sort of as context, talking about climate change, I'm going to focus our attention today, right, on an important pollutant, probably our most problematic air pollutant, and that's ozone, but at ground level, right? And we'll talk a little bit about how we find, and you probably know this, right? We find ozone. I don't want to go too far into this, get ahead of myself, right? But we find ozone at two places in the atmosphere. Well, off the ground, up in the stratosphere, which is actually, we call that good ozone because that's where we want it. It formed naturally. We want that ozone there. We'll talk about why a little bit later on. But we do not want ozone at the ground where we breathe it, right? It's got that one extra atom of oxygen, O3, versus the O2 that we breathe. That extra atom of oxygen is really problematic. So, and this is probably our most problematic pollutant. Okay, so I want to take just a minute because sometimes there's still a little bit of misconception when we're talking about climate change in terms of the difference between weather and climate. So I just want to briefly talk about that and the implications for those differences in terms of environmental problems, air quality in particular. So weather, right? When we're looking for getting the weather forecasts, right? We normally get that forecast for maybe today, right? Maybe tomorrow, maybe just a few days, right? And you know you're not going to trust it very much, say, after 5 days, right? Because it falls off, right? It gets less accurate after, say, 5 days. Now, I need to defend my profession, right? I'm a meteorologist and a geographer, but maybe more of a meteorologist at heart. We actually, out to about 2 or maybe 3 days, we do an awesome job these days. We're like about 9 to 98% accurate in shorter term forecasts. We get a bad rap, right? We're better than economists, right? I can tell you that. No offense to any economists out there, right? But we actually do a pretty decent job with short-term forecasts, which I appreciate as a pilot. One of my hobbies. I don't know if this was mentioned in my bio or not. That's actually how I got here, right? Right? Thank you. My true passion is flying, and so I appreciate the good forecast that the meteorologists do. And later on, I'm going to show you a little picture of my plane, because I can't help myself. It's my baby. I don't have kids, right? So my plane is kind of my baby, and I couldn't afford my plane if I had kids. That's for sure. But anyway, back to weather here, right? So when we're talking about weather, it's right. It's and a lot of my talk is going to be about space and time scales, right? So the temporal scale, the time scale for weather, it's a short period of time. And we're generally looking at a small geographic location, maybe a city, maybe the Cleveland metropolitan area, maybe this area of Ohio right there. That's weather. And, and these are the elements, variables, parameters, whatever you want to, refer to them, that we use to describe the condition, the state of the atmosphere at any point in time and at any place, right? Air, temperature, pressure, humidity, clouds, winds, precip, visibility, all the stuff, right, that you care about when you get in the weather forecast, right? I guess we're probably mainly concerned about air temperature, right? But, probably you hear about high and low pressure areas and that kind of thing, right? High pressure associated with good weather, low pressure, weather's going downhill. And that's, I'm going to digress here for just a moment, but looking ahead to, I can't help myself, right? Weather for the rest of the week, I'm here all week, so I'm really looking forward to the 4th of July. I just heard about a cool parade that I need to attend, right? So I'm kind of taking a look at a front and a low pressure area that's kind of heading our way, but I'm optimistic at this point in time. Right? I do my own weather forecast. I can't help myself, but then I take a look and see what the Weather Service has to say, because they do a really great job, right? All right. So, just another example of weather, right? So that's a weather map, right? And you got your lows and your cold front. The condition of the atmosphere in one place, at a small, relatively narrow point of time. Contrasting with climate, right? A lot of folks describe climate as, and this is kind of an apt a definition of climate, right? Average weather, right? So really long-term weather. As a matter of fact, when the climatologists, when they're taking a look at the climate of a place, right, they actually, the bare minimum of years of data that they look at, 30 years. We call it the 30-year normals, right? So a nice period, nice long trend. And also, when we're talking about climate, we're looking at a larger geographic area, so larger temporal and spatial scale. Really, with climate, it's trends. So I just kind of mention this because every now and then I will hear, we'll have, don't seem to have too many of these lately, but we might have a cooler than average summer in some location, right? And so you'll hear someone say, oh, this was a really cool or cold summer, so there's nothing to this climate change, right? But you can't just look at one summer, right? It's trends. I'll use the example with my students. I'll use a bowling example. And so I always ask them how many, so this is North Carolina, Greensboro, North Carolina, right? So I'll say, how many of you bowl? I might have one hand that goes shows up, right? Well, I'm from Milwaukee, right? For a long period of time. What do you do in the winter? You're not going to go outside, right? So you bowl, drink beer, and eat cheese. Pretty much it, right? So I like to use this bowling example, right? You know, I say, do we have any bowlers in here? Just one bowler? Okay. That's okay. You can be a golfer, right, with your handicap as well. Got some golfers in here? No golfers. Anyway, shuffleboard. I'm gonna try that tonight for the first time, and embarrass myself, I am sure. Right? But when you talk about your ability in one of these sports, right, you just don't look at one game. That would be weather, right? You take a look at your trend, your trajectory over time. That's climate, right? So I like to point that out, right? This is, for example, here we're talking about climate. These are global average temperatures. This is just a slide from one of my textbooks. Near sea level, right, we got the orange and the red. That's where temperatures are warmer, and the warmer temperatures are exactly where we'd expect them to be, right, near the equator. With colder temperatures to the north, right, colder temperatures to the north and then colder temperatures down toward Antarctica, right? So long-term period of record, average weather of a place. As a bit of an aside, right, climate is more than just averages. We also, with respect to climate, get into extremes as well. Like what's the greatest amount of rain that's fallen in 24 hours in, Lakeside, Ohio as an example? What's the greatest amount of snow you've ever had in Lakeside, Ohio? Anybody know what the largest, how much snowiest winter you ever had? Did you have any snow this past winter to speak of?
In 1918, I think it was, this area got hit with the so-called white hurricane.
The lake froze over. No?
It was more than that.
Okay.
I know Port Clinton had snow second-story windows.
Okay. Haven't seen that recently, have you?
No.
No, indeed. I just want to mention, so it's the extremes of climate, all right? Okay. So now that we have a sense for, climate, we know, and we're, beyond confident about all this, right? We know that a goodly amount of the warming that's taking place is from human activity, right? We know that Mother Nature changes the climate over time, but none of the so-called natural variability, right, like the amount of sunlight that's coming in from the sun, can't explain the warming that we are seeing, right? So before I get into air quality, I want to talk a little bit about, because if we're going to understand, right, how climate change is impacting the quality of the air that we breathe, right, I want to talk a little bit about the basis for anthropogenic, human-caused climate change, which is probably not a new topic for you folks, but I want to get into a little bit of the weeds on this. And also, I throw this slide up there just to make the point that the ultimate heat engine for the Earth is, and I'm looking up because it's up there, even though I can't see anything but the ceiling, right? I'm looking at the sun, right? Which you see a lot of these days, right? That's where we get our energy. Secondarily, we get some energy from the Earth's interior, right? That kind of escapes to the surface. That's, diddly squat in comparison to the energy that we get from the sun, right? So that's where we're getting our sunlight, right? And when we're talking about that sunlight in the context of human-caused anthropogenic climate change, right, we need to talk a little bit about the nature of the sunlight that we're receiving. Right? So I've thrown up in my students' eyes, always glaze over as soon as I bring up the electromagnetic spectrum, right? That's if they're not looking down at their cell phones, right? So most of our sunlight, let me remember to use my pointer here, right? Most of our sunlight, if I can get my pointer to work there, where's my pointer going to there? There we go. A little hard to see on the slide. There we go, right? Most of the sunlight that we receive is in the so-called visible part of the electromagnetic spectrum, right? This is where we say the sun sends out its most intense, most potent sunlight, right there, kind of in the green part of the spectrum, right? About 0.5 micrometers, millionths of a meter. I always tell my students, so a meter stick, probably comes up to here on me, something like that, right? So a millionth of that, right? That's the wavelength of sunlight that's most potent. The Earth and the atmosphere, and everything on the Earth and in the atmosphere, and including the oceans and everything, the Earth-atmosphere system, right? That sends forth energy at much longer wavelengths. Right? So I'm going to say this a bunch of times. Sun emits short-wave electromagnetic radiation. Right? Peak emission about 0.5 micrometers. Right? Earth-atmosphere system, much longer wavelength energy. And when I say wavelength, think an ocean wave, right? Where we got the ridges, right, or the peaks, right? And then we got the trough, ridge, and peak. When we're talking about wavelength of an ocean wave or wavelength of electromagnetic radiation, it's the distance from one wave crest to the adjacent wave crest, or from trough to trough, right? And the sun, really short wavelengths. Earth-atmosphere system, longer wavelengths. Plays a crucial role in anthropogenic warming and what's driving it, the enhancement of the greenhouse effect. Okay. So I just want to chat a little bit about that because we need that as our foundation for chatting about ozone, right? Pollution. Just as a quick example, right? This, let me use my slide there, shows up, there we go. Kind of lose it on the white right there, there you go. So this is, on this scale, we've got intensity of sunlight, solar radiation. We sometimes call it insolation, incoming solar radiation, not the pink stuff in your attic insolation, but incoming solar radiation, insolation, right? It's really intense, high peak, right? And that peak comes at much shorter wavelengths, about 0.5 micrometers, right? Okay, let's contrast that with the energy that the Earth-atmosphere system and everything in it, including you right now, including this carpet, including my water bottle, everything, the energy that system emits, right? Okay, where's that peak? Where's that? Oh my gosh, bless his heart. Whoa, way down here. So not very intense and at much longer wavelengths. I mean, 10 micrometers probably doesn't sound a lot longer than 0.5, but it is. Earth-atmosphere system, right, long wavelengths, sun, much shorter wavelengths. Crucial, crucial role in understanding the greenhouse effect and its connection to global warming, building into a discussion of air pollution, all right? So I bet you're familiar with some of these gases, right? Carbon dioxide, water vapor, nitrous oxide, methane, ozone. Sort of the fancy name for these are selective absorbers, but I bet you know them as what? The greenhouse gases, right? The more descriptive term is this selective absorbers, because kind of the bottom line here is that these gases, right, as the sunlight's coming in through space, then through the atmosphere, down toward the surface of the Earth, these gases really do a pathetic job at absorbing that sunlight. So maybe we should talk a little bit about the difference, though, between absorption, reflection, and transmission. So we got that sun, you got to picture this, right? You got that sun passing through the atmosphere on the way down to the surface of the Earth, right? And when various gases or whatever objects, get in the way of that sunlight, you got, what, 3 possibilities for what can happen to that sunlight, right? Sometimes that sunlight can pass right through the gases, transmitted right through the gases, which is what happens, right, with shortwave radiation, right, from the sun, where these gases transmitted right through them for the most part, right? And with transmission through, kind of like when light passes through water, right? You dive down into a pool, and if the water's pretty clean and everything, right? There's still some light down there, right? Because the light's being transmitted through that water, right? With transmission, right, no heating of the object occurs. Light's passing right through it. Okay? That's one possibility. Another possibility is that the light can bounce off of, reflect off of, or scatter off of some gas or some object, right? And with scattering reflection, no heating. Third possibility, absorption, right? That object can absorb that energy, be it long or short, right? And with absorption comes, I need a t-shirt that says this, right? Or tattoo now. Tattoos is not a good look for me, I don't think. But I always tell my students those tattoos that they got, think about this down the road, but that's, they don't listen to me. Anyway, with absorption comes heating. The object gets heated up, right? So since these gases here, right, allow the sunlight to pass right through them on the way down to the surface of the Earth, the gases don't get heated up. But with, next slide, okay. So on this side of the slide, find my cursor again, right? This is yellow sunlight, right? Shorter wavelength of energy coming down from the sun, reaching the surface of the Earth. Over here, we've got the longer wavelength energy. See how the waves are a little bit longer, right? And it's red. We like to use that for longer wavelength energy. With the longer wavelength energy, right, these gases, right, like carbon dioxide, water vapor, nitrous oxide, methane, and ozone, right, these gases actually absorb the energy that is leaving the surface of the Earth, right? So with that absorption, these gases get heated up, right? I'll sometimes make the analogy, right, of a blanket on a bed, right? So when it gets colder here in the winter, or you got the air conditioner turned up, right, too low, you need a blanket on the bed, right? Well, unless you put the blanket in the oven, or do the old camping trip of like, putting some hot stones on it or something like that, right? That blanket's going to be the same temperature as you or the room, right? So how does that blanket keep you warm? It's absorbing the long wave radiation coming off your body. You're acting like those greenhouse gases. And of course, the thicker the blanket, right, the better it absorbs. So that's how it's keeping you warm. So these gases, right, because they absorb at long wave radiation that the Earth and everything on the Earth is emitting, right, act to keep us warmer. So kind of it stands to reason, if you got a blanket that's getting kind of old and it's got kind of some holes or some thin areas, right? If you get a better blanket or, put some patches of quilt on the holes or something, right? You're filling all those holes, less long wave from you is going to escape and the blanket's going to keep you warmer. Sometimes I tell my students, this usually wakes them up because at this point they're like sound asleep or desperately want to use their phones, right? I can just see, it's kind of fun to watch me and kind of see they're getting all itchy if they're too far from their phones because I don't let them use their phones in class, although they try to take a sneak peek, they keep it underneath on their lap and I always say, what are you looking at down there? But anyway, right? I always tell them, well, suppose you're cuddling with someone. How is that cuddling person keeping you warm, right? I mean, they're probably got the same body temperature, right? What are you getting from them? Long wave radiation. And that kind of interests them. They go, oh, somebody to cuddle with. Anyway. All right. So we're just talking about, so really what we're talking about, this phenomenon of these gases, right, that absorb at long wavelengths but not short wavelengths, we call it the greenhouse effect. And thank goodness for the greenhouse effect. Keeps the average planet 59 degrees, well, it had been. This had been the average near surface temperature, global temperature, 59 degrees Fahrenheit. Warmer than it would be without the greenhouse effect, right? So thank goodness for this. But what we're doing by adding more of these greenhouse gases, right, is we're enhancing the greenhouse effect, right? So CO2 gets all the attention, right? Because that's the gas that we're emitting in the greatest amount into the atmosphere by burning fossil fuels. And I know we know that, right? But there's some other important ones as well, right? Water vapor. It's a greenhouse gas. And this is one of these positive feedback loops. So water evaporates more quickly when it's warmer. You raise the temperature, more liquid water gets converted to gaseous water in the atmosphere, right? So as we warm the planet up, we're getting more water vapor into the atmosphere, which is enhancing the greenhouse effect even more, right? So it's kind of a vicious positive loop. There's some others going on out there too that I might mention. They're just really kind of threatening, right? But I kind of want to look at this ozone down here, right? It's a greenhouse gas, right? and it's also a pollutant. So it's kind of a double-edged sword, right? We're getting more warming from the ozone, which we're going to see is helping to put more ground level ozone into the atmosphere. That's kind of why I'm focusing on ozone today. Tomorrow I'm going to talk more about particulate pollution. And I'll allude to that a little bit today. Okay. All right, just a quick slide. I'm going to move on along with some of these slides to move along here. This is just a slide showing you, and I thought you might find this pretty interesting. You're probably aware of this already, right? So in the top slide over here, we got CO2 concentration, right? And over here, we're moving forward in time to more recent time. And you can see right about kind of like after the 1800s, the amount of CO2 in the atmosphere is increasing exponentially. So what's driving that? Why are we seeing a tremendous spike right around early mid-1800s in the amount of CO2 going to the atmosphere? Fossil fuels, right? Exactly. And the slide on the bottom, right, we're just showing you there's a nice correlation between the amount of CO2 that we emit in the atmosphere and the actual CO2 concentration in the atmosphere, right? A good one-to-one concentration. It's not perfect because, and you may be aware of this, right, the oceans are a good sink for carbon dioxide. They absorb CO2 quite readily. But there is sort of like a threshold amount of CO2 that the oceans can absorb, and we know in the past there have been times where CO2 has been rapidly released in the atmosphere, and so rapid warming. So we're kind of concerned about that as well. All right. So with hopefully a decent understanding of what's driving anthropogenic climate change, we can move into a discussion of air quality. So, and again, we got more severe weather, more frequent, more intense severe weather. Of course, we got heat waves. And we're going to talk about, if not today, on Wednesday, heat domes. That's a kind of a new term that the media is using, and the National Weather Service is kind of climbing on board with this term as well. Everything kind of has a fancy name these days, right? Winter storms get names now they never used to. I guess it's maybe easier for us to keep track of. And of course, wildfires, right? Yeah, I was in, I think you folks had some pretty bad effects from this last year during the summer. The horrific wildfires in Canada. The eastern seaboard, it was just, air quality was just miserable. I mean, you could smell the smoke in the air. And we're going to talk more about wildfires and the kind of pollution associated with wildfires, a wide array of pollutants, primarily small particles, which we refer to as particulates. In case I forget to mention this later on, when we use the term particulates, or PM, the abbreviation particulate matter, we're talking about solid particles in the air, but also liquid droplets in the air as well. Both are considered particulates. We sometimes use the term aerosols as well for particulate matter. Okay. So what then are the connections between a warmer planet and air quality? Well, like everything in life, it's complicated, right? And there's a whole lot of chemistry going on here as well. And I'm not a chemist. Had to take, there is a branch of meteorology where you can specialize in chemistry. That wasn't my thing. Do we have any chemists in here? Oh God, now I got to watch myself carefully. Feel free to correct me if I'm off here. I was more. You could kind of do the meteorology. It's physics and chemistry. The physics kind of worked for me a little bit better. I did date a couple of chemists once. Didn't work out so well. They both dumped me. I don't know what that's about. Smarter than me probably. Anyway, so it's complicated. All right. So what makes air quality issues so challenging is that it's just not the yuck that we put into the air. It's not that simple. You can't control air quality just by, it helps most certainly by lessening the amount of pollution that goes in the air. The meteorology of the atmosphere, right, plays a huge role. The kinds of weather systems. And I'm a meteorologist. I love that stuff, so I want to chat about that a little bit eventually, right? So it's both meteorology, high, low pressure systems, inversions, really cool stuff. I get into this, right? Can We all have our things, right? Anyway, so the meteorology plays a role. So I want to talk a little bit about the atmosphere, right, if we're going to understand air pollution. So I often do this with my students. I will make them come outside. It's painful for them. They don't want to be outside. They want to be in, particularly the COVID kids. Ooh, they're just a mess these days. It makes it challenging, a number of levels. They say, can't we see this on our computer screen? No, you got to go outside, right? You got to see all this. So, I look up, right, and to them, and to me, right, maybe more, it looks like the atmosphere goes on forever, right? We think it's pretty extensive, right? Pretty voluminous, right? That it can handle whatever we put into it, right? Well, that's not really the case. It's actually kind of thin and fragile, right? It does extend up to 480 kilometers, right? Which sounds like a lot, but this slide gets to the fact, and its title here, caption, where the heck you want to call it, vertical structure, right? Most of the gas in the atmosphere. Anybody know what the two predominant gases are? I was going to have a slide, but then too many slides. Anybody know what the two predominant gases are in the atmosphere? So you take a, just breathe in. Oxygen, right, about 21%. What's the big one? What's the 10,000-pound gorilla? Nitrogen, yep, N2, right? It's about 78%. Remembering that. 78 and 21, I can't remember many numbers at this age, right? 78 and 21, that's pretty darn close to 100, right? It's like 99 point something. Well, it's not, is 99, right? So there's not a lot of room for much else. But most of those gases, right, are held close to the surface of the Earth. Right? That's where most of the air is. So that's really where most of our atmosphere is. And everybody in all the textbooks, right, for scale, for perspective. Let me find there we go, my pointer again, right? Mount Everest, which is, I had to look this up because I can't remember numbers, right? About 24,000 feet. Anybody climb it recently? Not recently? I don't know. Some days I think about that, but I don't know. Too cold now. I don't like the cold so much anymore, right? But, right, and if you climb, go far enough above sea level, right? You find yourself kind of huffing and puffing, right? Because there's just not much air, oxygen there, right? So most of the gases, right, are pretty close. Like, I always remember this in terms of kilometers. So you got to do the conversion in miles, right? Like maybe 10 to 12 kilometers off the ground. That's where most of the gas in the atmosphere is. Go up to, see this point right here where it says 50%, right? Half of the atmosphere is below, that level, which is not very high up, right? So when we emit pollutants in the atmosphere, they can't be diluted, right? Used to be just a quick aside. Maybe it'll help to make this point. We used to say, and I kind of used to mention this in terms of river pollution. I had a hydrologist friend who used to teach a lot about this, and he would always say, well, the solution to pollution is to dilution, right? Back in the day, when you had just a few factories along rivers and whatnot, where did they get rid of their yuck? Right in the river, right? And the river could handle it. It wasn't a good thing, right? But the river could handle it because plenty of water to dilute it, right? Well, with respect to the atmosphere, if we had 480 kilometers of actual gases, we could dilute it, but it's not. It's close to the ground, right? So the atmosphere is not as extensive as we think. This is just the meteorologist and me showing you the vertical structure of the atmosphere by temperature, and it shows you. Get my thing going here, losing it right. This layer right here, right? This is where the vast majority of the gas in the atmosphere is. And we call maybe you've heard of this layer, the troposphere. Its nickname is the weather sphere because this is where weather occurs in the lowest 10-ish or so kilometers, right? So that's all the atmosphere we have to work with. And we're going to need this information later on, but this shows you how temperature changes. There we go, in the vertical, this red line. And notice that it's warmer to the right down here, right? So how's temperature behaving on average, in the slowest most layer? It's decreasing with height, isn't it? And that's going to play a role in the meteorology of air pollution down the road. The atmosphere on average in the lowest kilometer where most of the gases are decreases on average. On average, though, okay. As a matter of fact, and here's a number for you. I don't think we really need this, but this is the average, and we got a mountain for perspective. This is the average temperature decrease. We call it the lapse rate with height. 3.5 degrees Fahrenheit for every 1,000 feet. But you kind of know that the atmosphere does this because besides having to breathe hard when you climb a mountain, what do you need to throw on? A jacket. In North Carolina, anyone been to Asheville, North Carolina? Yeah, everybody knows Asheville. It's a special place. It's getting kind of busy and more people and getting more expensive, unfortunately. But it's, gorgeous mountains, a great place to live. Well, people, particularly from Florida, flock to Asheville in the summer because you're at elevation. It's cool, right? Okay, again, just to give you context here, we're building toward, continuing to discuss air pollution in general, ozone in particular, but we're looking at how meteorology, the atmosphere and weather systems affect air pollution. 3.5 degrees Fahrenheit, but you don't have to worry about that number. Just remember that on average, the temperature falls off, lapses with height in that weather sphere. Okay, so hopefully by now, you kind of picked up on that the atmosphere, it's not all that extensive, right? Most of the gases in the atmosphere are close to the ground, right? And hard to kind of fathom because you think there's a lot of air out there, but we're actually changing the composition. And we've been changing the composition, big time since the start of the Industrial Revolution, but it's only getting worse because there are more and more people, and where are those people living? Where's everybody moving to now? The cities, right? And that trend is only getting exacerbated, right? And so when folks live in cities and do what they do, drive, use their air conditioners, have industry or whatnot, you're taking that air pollution and concentrating it into a smaller geographic area. So there's even less ability of the atmosphere to dilute that pollution, right? And that trend is only getting exacerbated. And remember my theme early on that first slide? And global warming is only making it worse. So anyway, just you got on the upper left there, right? You got some power plants, right? Probably burning fossil fuels, probably coal, right? The dirtiest fossil fuel. And then you got transportation in the middle, our cars and trucks and buses and yada yada. And then that's an old photo from Chicago in 1995. But you still, if you fly commercially, I've got a slide later on, actually, my plane, you can see this in my plane, right? But when you're flying up high, 35, 40,000 feet or whatnot, right? And then you're starting to descend to land in an urban area, what do you notice happens to that big, beautiful blue sky? What you're seeing in Chicago there, right? Right? You're seeing the various pollutants. Okay. So I like to mention, because people get a bad rap, right? Talking about anthropogenic pollution. We kind of forget that Mother Nature can be kind of dirty herself, right? A lot of natural pollution, right? That could be somewhere in Iceland. I don't recall where the heck I got this particular slide, but it's a volcanic eruption, right? And from volcanoes you get, right? These are some of the, right? Volcanoes, right, actually produce a greater quantity of air pollution than humans do. Right? Volcanoes, for example, have oxides of sulfur, right? Common one, sulfur dioxide, but a bunch of other oxides as well. There are the particulates, liquid and solid particles, right? Forest fires. More forest fires these days, right? Because we're warming the planet, everything's getting drier, right? CO, carbon monoxide. My subscripts are screwed up here. I was having a hard time getting them right, and I just kind of gave up. CO2, nitrogen dioxide, particulates, plants, they pollute as well. This is actually a big source of natural pollution in North Carolina because of our pine trees. Not exactly sure why that is, but a lot of hydrocarbons. Well, hydrocarbons, so that classic example, hydrogen and carbon, classic example would be the gasoline, petroleum, right? Those are long chains of hydrogen and carbon. Pollen from plants, right? Yeah, if you do move to North Carolina, ever decide to retire there, just beware of the pollen. It's bad. It is bad. Brief aside there. All right, CH4, methane, hydrogen sulfide, right? Soil dust, various viruses, and then the ocean, right? So all natural sources of pollution, but Mother Nature does it right. Mother Nature's pollution is generally not problematic because she spreads it out, right? So you've got more atmosphere to dilute that pollution. Tends not to be, I mean, in certain circumstances like volcanic eruption, yes, right? But sort of globally thinking, long-term thinking, she spreads it out. Unlike people, right? We live in concentrated geographic areas. And that's really the big problem with anthropogenic pollutant. So these are some of the big human-produced pollutants, right? And you see many of the same natural pollutants are on this list right here, right? Like carbon monoxide, nitrogen oxides, hydrocarbons, ozone, and then PAN, it's peroxidic, I don't know, it goes on for, I don't want to put you on the spot in my chemistry. Do you know what PAN stands for? You might not. Yeah, peroxidic something, everybody just calls it PAN. Good. Particles, right? CO2, water vapor, methane, right? So these are all the human pollution, human cause pollutants, right? Let's see, there's a picture of another. So there we go. I'm going to come back to that other slide. Oops. Okay. I guess I want to chat a little bit about this. So want to classify air pollution. And we put stuff, most of my students, right? We put stuff into categories in order to understand things, right? But, and the students always want these nice, clean categories, right? With no overlap, right? They want nice, sharp edges. And it drives them crazy, right? When things bleed over the edges, when it's not black and white, right? Usually by the time they're a grad student, they appreciate the grays in life, right? So anyway, to understand pollutants, we put them into these neat little boxes, but a lot of overlap here, right? So one of the categories that we like to put pollutants in, primary pollutants, right? So they come directly from identifiable sources, like directly out of the tailpipe of your car, or out of a smokestack, or some other form of industry. And the image that always comes to mind for me is, and I'm sure for you, perhaps you've experienced this as well, you're behind, and we're doing a better job now, our sources of transportation are getting cleaner, but you're behind an old bus or an old diesel-burning truck, right? Big old tailpipe, right? And it's right there in your face, and yep, all sorts of soot particulate matter is coming out, right? And you're breathing it, unless you hit the air conditioning button on there, maybe your filters are working good, right? But that's a primary pollutant, right out of the source, right? So we've got primary pollutants, and we're doing mainly through regulation and technology as well. And the regulation is largely through the Clean Air Act. Anybody know when the Clean Air Act and Clean Water Act, I might have my exact year wrong here, but came out? Yeah, 72-ish, I think. I think there was some movement in 69, so a long time ago. Hasn't been updated, as Congress has had a real hard time updating, right? But anyway, those regulations have been really helpful in cleaning up primary pollutants, in part because, well, you know the source, right? Same thing with water pollution, right? If you can identify the source, you can clean it up. But it's more challenging with our other class of pollutants, which I'll get to in a second. So on the left, the pie chart, love pie charts. You got some of the primary pollutants, the major primary pollutants, right? And you can see one's carbon monoxide. We've done a pretty good job of cleaning up carbon monoxide. Nitrogen oxides, right, a big player. Sulfur oxides, and then volatile organic compounds. Same thing as hydrocarbons, we use the term, and then particulate matter, right? And where does that stuff come from? What is the 10,000-pound gorilla? Transportation, right? And then you got, so the fuel combustion and stationary sources, that's power plants, right? A big player as well, and then industrial processes as well. But again, we're doing a pretty good job at these primary pollutants. What's really challenging, because there's a lot of chemistry going on here, which a lot of reactions, and I don't think they're completely understood by the atmospheric chemists, right? Secondary pollutants. So here the primary pollutants come out, and then they interact, right? Kind of misbehave together, often in the presence of sunlight, strong sunlight and high temperatures. Climate change, warming globe, strong sunlight, higher temperatures, right? And they form. And ozone is a secondary pollutant. Right? Talk more about that, right? So I had a slide I'd like to show us a little blurry. Could be my eyes, who knows? Anyway, so here you got cars, right? Trucks, whatnot, right? And stuff come out of the tailpipe here, and all that stuff is kind of hanging around right above the ground, right? Call it the photochemical stew or soup. All sorts of ugly, nasty sorts of species right here. And then here's really strong sunlight, right? And then you get some secondary pollutants like ozone over here. And there it is, that's pan. Yeah, I'm not even gonna try to read that, right? We're gonna focus on this ozone, right? So it's a secondary pollutant. You need the primary pollutants to interact with the sunlight, which is why ozone has a season, right? Ground level ozone. We don't even worry about it until, well, we're starting to worry about it sooner and sooner because the hotter temperatures are coming earlier and earlier in the year. But I think we start monitoring, so the states are actually responsible, systems set up so that the states are actually responsible for monitoring pollution and then coming up with plans if the federal EPA decides, yeah, you are emitting too much pollution, then they mandate that at the local level, state and sometimes county agencies, that they come up with a plan to reduce the air pollution, right? So it kind of gets passed down. If the state, and some states are better than this at others, states in the Midwest do a better job. We've kind of, North Carolina is pretty good. Some of the southeastern states, not so good at all. So coming up with, they'll be told, they'll be told that, you're exceeding pollution standards, and you got to do something about it. You got to come up with a plan that we'll accept. Well, they'll drag their feet, it'll go to court or whatnot, and eventually, if the EPA wins the court case, then they will come up with a plan for the state. That's kind of how that works. But anyway, ozone is one of those secondary pollutants. Okay. Just some other terms in the area of air pollution that we use that you might be familiar with, and you're probably familiar with this one, right? Smog. It's kind of a catch-all term that we use. I thought you might like the derivation of this particular plan, right? And when you're thinking smog, right, you might be thinking days of past, right? When it was a little bit more problematic, but we got smog today, right? But think London, right? And we call this industrial smog, right? It comes from smoke plus fog. So the smoke is particles, and what were they burning here? So coal and wood, right? And so some really nasty in this particular example. London during December of '52, right? Visibilities were often restricted to less than 100 feet, and streetlights needed to be turned on. So we don't have these scenes anymore, at least in North America and much of Europe, but maybe you've seen scenes, I haven't heard so much for the last couple of years, because they're starting to get their act together. What part of the world were you hearing about really bad episodes of smog? China, right? Burning a lot of really dirty coal, high sulfur coal, right? They're kind of getting their act together because they realize that they can't go on doing that. Really? Okay. 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 So they're catching up fast. Catching up fast, right? So there's the old-fashioned smog where particles are involved, and so what I want to chat about again is ozone, and that's photochemical smog, right? So it's where the primary pollutants are emitted, they interact with sunlight, right? And so that's the photochemical part of this, right? Sunlight, photo, and the chemistry going on. So some examples of, right, photochemical smog: nitrogen dioxide, right? And then ozone. And again, I'm going to focus on ozone at ground levels. So ozone, bless his heart, right? How is it harmful? Maybe a little bit of context, a little anecdote here for you. I have been interested in ozone for quite a while. I don't do that much research anymore. Now I'm undergraduate director and do a lot of teaching and those sorts of things. It's kind of where my passion is. is now at this stage in my career, but back when I was working on my PhD and whatnot and had to get published and all those sorts of things, of course I'm doing a lot more research, and I got fascinated in ozone. I was living in Milwaukee at the time, going to the University of Wisconsin, Milwaukee, and I run a lot, was doing a lot of running along the lake, and I would realize that there were some days air quality looked fine to me. I couldn't see anything. The air looked nice. Didn't see any particulate, any of that classic smog. I'd finish my run, like, just a little bit wheezing here, like, this is just something's off here. So I took a look at the air quality report for that given day, and said, yep, ozone was really high. So what happens in Milwaukee and other large lake areas, and this is why I love the two disciplines that I'm in, geography and meteorology, because that's what's going on here, right? Milwaukee's pretty industrial, not like it used to be, right? But to itself, along Lake Michigan, there's a pretty big industrial area, right? You got Chicago, and then you got the Gary area, not the industry that it used to have, right? But it's still producing a whole lot of pollution. Well, that pollution gets transported by winds coming from the south, we call, say, southerly winds, right? Brought up to the Milwaukee area, right? And then, I'm going to talk a little bit more about this later on, but that pollution would get brought out over the lake, so it's kind of sitting there in the early morning hours, and the sun's heating it all up. You're creating this photochemical pollution, and then under the right conditions, the winds will bring that pollution right back on shore to Milwaukee. And ozone is odorless, tasteless, and completely invisible. You don't know it's there. It's kind of insidious. So just a quick aside, well, this is actually good gas, water vapor, but water vapor is the same way. It always kind of boggles my students' mind, right? Water vapor, right, you can't see it, you can't taste it, you can't smell it. It's completely invisible. If you're seeing it, it's either liquid or solid. I digress there, right? Anyway, so it forms, right, ozone forms as a secondary pollutant, right, when oxides of nitrogen and these hydrocarbons or volatile organics, as they're sometimes called, chemically react in the presence of sunlight. I think the next slide up, yep, hey, I remembered my slide. I don't know how the heck I did that. Anyway, a little graphic. In a very simplistic sense. It's much more complex than this, so I apologize to the chemists out there, right? So here's kind of the scenario for this. So it's a summer day, here in Lakeside, Ohio. It will be in a big urban area where we've got more sources of pollution. So any big urban area, right? So you get up in the morning. It's going to be a hot day, right? It's going to be, pretty sunny day on the whole. Maybe a few clouds, but good sunlight, good strong shortwave energy coming from the sun. So you get up and you fire up your car, all right? And you got those primary pollutants coming out of your tailpipe. And what you're actually making some of this oxides of nitrogen. The N2 in the atmosphere, right, through the high temperatures in your engine and also out of the exhaust, convert that to various oxides of nitrogen. So that's going into the air, right, just by firing up your engine. And it's sitting there, right? If the overall atmospheric conditions are not too windy, right, there's not a lot of ventilation. It's just got to sit there, right? And then, right, you look at your gas gauge, right, like, oh, I got to get some gas. You don't have one of those electric vehicles. You got to get some gas, right? So you get gas, and you pump in the gas, right? And you can smell gasoline, can't you? You can always smell a little bit, right? Right? And on the pump, what do they put on the pump to try to keep some of that gasoline from evaporating? Those little flappy things. And I haven't gotten into gas in this area. So in some places where air quality is poor, high levels of ozone and other pollutants, they'll have the more sophisticated vapor capture things, those big, like, long kind of rubber sorts of things. I know they have them in California, and I think they might have had them in Milwaukee. We don't have them in North Carolina. They certainly don't have them in Alabama or Mississippi, right? Right, because they don't have an air pollution problem, because they don't monitor for it, right? So there, yeah, that's kind of how it is, right? You don't monitor for years, fine and dandy, right? Anyway, but some's going to escape, right? So you got those hydrocarbons, volatile organics, going out in there in the atmosphere as well. And what they do is, right, they're all kind of hanging out, sunlight's getting stronger, and they get converted into ozone, right? And that's building up throughout the midday into the early afternoon, right? Now, I might forget to mention this later on, but some ways to avoid all of this is to fill your car up at night, because at night there's no strong sunlight, so you're not going to build up the amount of ozone, right? Or you can drive an electric vehicle. I mean, there'll be some ozone produced at the power plant, right? But that can be controlled to a greater extent, right? So they often say that, right, these pollutants bake together in direct sunlight forming ozone. So that's ground level ozone. Okay, so you may have seen something like this, right? And the FAA has come up, they kind of stole our color coding kind of thing. We came up with this first, right? So this is the Environmental Protection Agency, their air quality division, right? They came up with their air quality index, and it's color coded, right? And well, if it's during the summer season, right, when they're monitoring for ozone, right, the air quality index will include both, consider both ozone plus particulate. They don't separate it out. Now you can go, some states are better than other states. Most states are pretty good now. I tried to take a quick look at Ohio, and they did a pretty good job with their website. You can actually see in real time what the values are for both particulates and ozone in most areas. Today's a moderate day for particulate around here, by the way. Not a bad day for ozone around here. I noticed that. And I think it was for this area. I don't think it was for the Cleveland area, right? But it's a kind of color-coded scheme that comes up that will handle both particulate and ozone. If it's during the non-ozone season, so during the cooler months of the year, it's just going to be particulate. Particulates are affected by the weather, and we'll talk about that, but they don't have a true season like ozone does, right? So generally, you're good in green and yellow, right? It's when you get to orange. And so a value of 100 and above, really, I guess really 101 on this scale, right, is considered to be unacceptable. Or the EPA will use the term non-attainment, right? And they're exceeding values that they shouldn't for ozone and for particulates. When you get down to the reds, the purple, and the, what is that, I don't know, kind of rust colored here, you're getting to really nasty levels of particulates and ozone. Right. So the EPA, just a little bit about how the EPA classifies ozone. Thought you might find that interesting. So back when I started studying ozone, was working on my, excuse me. Oh, there it is. I haven't talked for a long time since late April, so I'm realizing that now. It's great. In North Carolina, we get out. Now it's like the last week of April. It's like, oh my God, that's great. I'm going to start back, though. And I guess you guys do the same thing here. Schools start back mid-August. Is this correct? It used to be, when I lived in this part of the country, it was Labor Day. How did you allow that to happen to yourselves? It's just ruined summer. Right here is Labor Day? Wow. I want to teach here. Oh, there you go. Okay. Anyway, back to when I was working on my dissertation in Milwaukee, working on ozone. The EPA was more concerned about ozone if it would kind of spike during the day. If you had, 1 or more hours where it'd be super, super high. The value back then, if I'm recalling correctly, was like 120 or 125, say ppb, which is parts of ozone per billion parts of the rest of the air, right? That's what health studies at the time showed, that really it was only problematic, had significant health effects if you had these really high values. Well, the EPA did its job. They're supposed to conduct new studies on human health, and they realized that at lower values, even at lower values, but over a longer period of time, there were significant health effects, particularly to the elderly and folks with pre-existing health conditions, right? Lung problems, cardiac problems, asthma, and the folks working out of doors, right? Doing the hard work all day long, right? So the new standard, which is, I don't know, maybe 10 or 15 years old now or something like that, what they do is, right, if an area meets the ozone standard, it's said to be in attainment, which is good, right? And the area doesn't need to come up with new plans to reduce ozone levels, right? But what they do is they take the fourth highest maximum daily 8-hour ozone concentration. So it's averaged over 8 hours, longer period of time, and the value is at 70 parts of ozone per billion parts of air. And it's averaged over 3 years, which will account for the fact that meteorology, weather conditions, which we're going to get to, play a role. Warmer summers, for example, right? So you might not be emitting any more pollution, primary pollutants, right? But the atmospheric conditions are such that you'll have higher ozone levels. So this kind of averages out those sorts of conditions. And we call that the primary 8-hour standard. They also have secondary standards. So primary standards are for human health, right, which is what they're most concerned about. But ozone also does a number on our products, right? It's harmful to rubber and fabrics, the paint job on your car, right? Also to crops. I always found it interesting, North Carolina, it did a real number on tobacco crops, which kind of didn't bother me so much, but the tobacco farmers, right, didn't like that at all, right? So essentially, on their air quality index, right, ozone corresponds to levels that are going to be above that 70 ppb. Okay? That's kind of how that's sort of how that is set in a somewhat simplistic way. I kind of alluded this to, so states are responsible for monitoring. So you can get, this is North Carolina, I just picked this up with, back in June 22, actually not all that long ago. So you can see, so this is a forecast. You can get forecasts for air quality, right? In different entities, state EPAs do this, sometimes county level monitoring systems will do this. You get a forecast for air quality, and you can also go ahead and get the actual conditions, right? This was the condition 622.24, ozone hourly, and there's some air temp thrown in there as well, right? So yeah, I always, before I'm running or whatnot, I'll go ahead and check the air quality levels. EPA is doing a good job, and the states are generally doing a good job. So you might be, we've got a nice watchdog agency keeping track of air quality, right? The American Lung Association. So I wanted to share some of their findings with you regarding ozone. And I mentioned that with respect to old industrial smog and many of the primary pollutants, doing a pretty good job at lessening those amounts and cleaning up the air. The secondary pollutants, in particular ozone, it's more problematic. So each year the American Lung Association issues a report card for ozone and particulate matter. So the PM is particulate matter, and I'm going to say more about PM tomorrow. But there are two kinds of PM, sort of two levels of particulate matter that we're concerned about. There's PM 2.5, which is 2.5 micrograms. Yeah, micrograms. That's a really fine stuff that you cannot see. And this is the PM that health officials are most concerned about because you can breathe it really deeply into your lungs, right? And studies have shown that it's the PM 2.5 that's most problematic. The other is PM 10. That's 10 micrograms and larger. And that's stuff that you can even see sometimes and are, to my understanding, the human body can kind of filter that out a little bit better than the finer sorts of stuff, right? But anyway, the American Lung Association issues a report card on both ozone and PM 2.5. And, right, the most recent report, which covered 2020, 2021, and 2022, right, some 100.6 million people lived in 125 counties in 26 states. It's pretty broad geographically, but we're going to narrow that down a little bit. that earn the F grade for ozone. Essentially, that means they weren't in attainment in those areas for ozone, right? So 3 out of every 10 people, including 22.5 million infants, right? And remember, it's ozone. It's younger folks and the elderly, and those with pre-existing health conditions that have the greatest impact on their health, right? 15.5 million people age 65 and older, and tens of millions of other individuals in high-risk groups who are exposed to unsafe levels of ozone pollution. So it's still quite problematic. Okay. Some good news. I'll take a sip of water on the good news. Let you think about some good news after some depressing sorts of stuff. So, the good news. One trend in the 2024 State of the Airport, this is the American Lung Association, shows that ozone levels, especially in the, here's where we get into geography, in the eastern U.S., are moving in a positive direction. All right? For the 4th consecutive report, the number of people living in counties with a failing grade for ozone declined. Right? This year by 2.4 million people. That's not insignificant. And we attribute this to the transition away from coal-fired plants. Right? In my neighborhood in North Carolina, my neck of the woods in North Carolina, I live in Greensboro. We've got one of the largest power plants in the country. It's the Blues Lake Power Plant. It's called the Blues Lake Power Plant because they created this lake so that they could use it as a cooling mechanism for their power plant. And they also dumped some nasty stuff in there. But anyway, the state's been fighting with them to switch from coal to natural gas, and they finally have a dual fuel system now, right? So that's helping, right? Switching to natural gas. It's not a panacea, but it's better than coal, right? Also, we're moving more toward renewable sources of energy, right? Transitioning different forms of, different kinds of engines, more electric engines now, and different sources of fuels and industrial processes, nationwide. So that's what they attribute to the positive trend in ozone pollution. Back to bad news. Right? They're doing a good job in the east. In the west, not so much. Right? The worst ozone problems confirms a pattern seen over nearly a decade of reporting by the American Lung Association. Right? The great majority of Western cities, right? So in the West and the Southwest, continue to dominate the list of the most ozone-polluted cities. California, right? Number 1. It's done a good job in some areas, right? But it's still struggling in ozone, right? California retains its position as being the state with the most metro areas on the list, with 10 of the 25 most polluted cities. The 6 states of Arizona, Colorado, Nevada, New Mexico, Texas, and Utah accounted for 12 others. So I think the next slide has the why of the disparity in geographical distribution. The East improving, the West not so much. What might be going on there? There are more people moving there, and the heat, and the greater amount of sunshine, which yeah, there we go. And then the geographical and meteorological aspects, which we're going to get into down the road as well. But is this a slide? Yeah. So reduction of ozone precursors has been effective. So oxides of nitrogen, right, and volatile organic compounds have been effective at reducing ozone concentrations. Those gains are now being offset by climate change, particularly in the West. Higher temperatures, drier conditions, sunnier skies, and the meteorology part of this that I'm going to get to, it's my favorite part, more frequent stagnation events, contributing to more unhealthy ozone days than would be otherwise. Right? So climate change is undercutting the progress we would have made. Right? So this is where global warming is just compounding issues. I have an analogy that I like to use. I'm going to watch my time a little bit. So don't let me forget to get to, I don't want to, I'm kind of proud of myself for coming up with this analogy. I probably saw it somewhere else and am forgetting it. I'm probably stealing it from someone and don't remember. But anyway, I'm going to save that one for you. Okay, so now I want to talk about how warming in certain geographic areas, right, is contributing to climate change, right, which is exacerbating our air pollution problem. So kind of getting into the meteorology part of things. And also I wanted to touch on things that you hear about, and I'm not sure if you're familiar with how some of these things work. Urban heat island effect. Who's heard of that before? A bunch of you have, okay. UHI, right? And you got this slide here that's showing you as we go from on this side, we got a rural area, right, and the suburbs, right? And here's the inner city, so the suburbs here, and now we're out to the more rural sorts of areas. Temperature on this scale on the left over here, right? And you can see that we have this, right, warmer temperatures on average in the urban areas. And with warmer temperatures, right, we're emitting more pollution into the air. We're running our air conditioners harder, right? More emissions at power plants and whatnot, and all other sorts of other associated factors, right? So urban microclimates are warmer on average than areas in the surrounding countryside. But so I don't forget to mention this. Yeah, so it's hotter during the day in cities. I mean, you know that. You spend time in cities, right? Right? It's hotter on average during the day, which is bad, right? But what's really problematic on a number of factors is it's warmer at night, right? The minimums are elevated at night. So it never cools off, which greatly impacts the population, right? They need to cool off at night if you don't have the air conditioner or whatnot. And so this impacts the folks that are, have the fewer resources, right? Might not have air conditioning, might be working outside, right? It's the higher minimums that are really problematic with the urban heat island effect. So I just want to take a look here in the next few slides at what is generating the warmer temperatures in the urban areas, right? And I think a lot of it is probably intuitive for you, right? So urban surfaces, well, urban surfaces it's concrete, right? It's tar, it's metal, right? These materials are much more conduct heat, right? So the sun's shining down, warming up the ground, right? It's really, the atmosphere doesn't get warmed by the sun, right? It's the ground that then shares that heat energy with the overlying atmosphere, right? So that energy gets transmitted down into the ground, gets stored in these, concrete and tar and all those sorts of things, and then is released to the overlying, atmosphere, right? So they're more conductive, and they also store that heat better as well. During the nighttime hours, because this stuff kind of fascinates me, if I'm walking through an urban area, I'll feel the different materials, and I'll see which ones are warmer, right? Which ones are storing that heat better, right? So urban areas, higher maxes, right, and higher mins. And again, it's the mins that are most problematic. Also, yeah, maybe you've heard that term albedo before. Sounds like an Italian hitman, doesn't it, albedo? It's a synonym for reflectivity, okay? So earlier we talked about when the sunlight, shortwave radiation, strikes an object, three things can happen to it. One is it can be transmitted through, no heating. Absorption is another, where there's heating occurs. The third was reflectivity, which our term for that, the reflectivity of the object is its albedo, right? So with reflectivity, no energy is absorbed. Well, urban areas have lower reflectivity. They reflect less, absorb more, so they get hotter. There you go, right? So that means that they've got more energy from the sun. The fancy term we use is net radiation, just radiant energy coming from the sun. They got more of that energy to kind of work with, to spend, right? And what urban areas do, they tend to spend it on heating stuff up. We call it sensible heat energy. Heat that you can sense, you can feel, or measure with a thermometer, right? Versus, and I think this might be with the next slide, just a quick slide on albedo, right? So snow, we know, is reflective, right? Color plays a big role in reflectivity. There are other factors as well, right? But we put that leaf there, right? Leaf is darker, it absorbs more sunlight, so see how it's melted the snow around it, right? So urban areas tend to reflect the sunlight. They're absorbing less, so they tend to be, or urban areas are absorbing more, so they tend to be warmer. Also, this is a big factor in urban areas. When it rains, where's the water go? Not into the ground, right? Storm sewers, right? And that water goes right to lakes and streams, right? So that means that there's no water in the ground to evaporate into the air. And to change liquid water, right, it might be in the ground, to gaseous water vapor in the air, it takes a lot of energy. To go from the liquid phase to the gaseous phase, a lot of energy. I always tell my students that gaseous water is like water on crack. It's zipping and dancing, not that I know what that is, but zipping and dancing around everywhere. It takes a lot of energy. So if you've got water on the surface that you can evaporate, like you might have in a forest, right, or plants, transpiration, right, you can use some of that energy that would have been used as sensible heat energy for evaporation, right? So that's why urban areas are considerably warmer, because there's less water to evaporate, to cool. I always remind my students, use the example with respect to evaporation and how it takes energy to cooling process. You go swimming, and some person steals your towel, and this could be a day where it's a little bit on the cool side, right? So you're just dripping wet, right? After a while, if you don't dry off, what do you get? You get kind of cold, right? Because all that water in your skin and your hair, it's evaporating. It's a cooling process, right? It takes a lot of energy to evaporate liquid water to gas, right? And you don't have that water in an urban area. That plays a big, big, big role, right? And you kind of know this, right? When you go into a park in an urban area, it's like, it's just so. You got the shade from the trees, but a big part of that is you got evaporation going on, less energy to raise a sensible amount of sensible heat energy. This slide kind of gets to that a little bit. So on the left, this is energy coming from the sun, right? Some of that energy is going to go into the ground to heat up the ground, right? Some of it's going to heat up the overlying air, sensible heat energy, right? But over here, if you've got some water, some of that energy is going to be used to evaporate the water, so it's not going to get as hot. Also, the geometry of a city plays a role. Got all these weird angles, right? So it's the sunlight, shortwave radiation, incoming solar radiation, it actually gets trapped, conducted down to the surface, kind of ping-ponged around a little bit, eventually down to the surface, keeps the city a little bit warmer, right? Also, you got people doing what people do, driving cars. Cars are hot, right? You got air conditioners going. You got your stoves on, everything people do, right? Releases heat energy, so that exacerbates the urban heat island as well, right? So this is all, so you got a warmer planet because of climate change. Now you got urban heat island on top of that, exacerbating things. And again, the warmer the temperatures, the more pollution that you're going to have in the air, particularly with ozone and a bunch of particulates as well. Sorry, part of this slide got cut off as well, right? Just a quick aside here. I'm just kind of getting at the point. So besides more air pollution being in the city and warmer temperatures, we also have more particulate pollution, and those little particles get carried up into the atmosphere, and gaseous water likes to condense on them, right? And it actually can help to produce precipitation. And so areas typically downwind of a city will have higher amounts of rainfall. You might remember the old cloud seeding experiments that you heard about way back when. Airplanes would, it was kind of a rudimentary process, that had these fine little particles. I think they used silver iodide. They kind of shovel it out of the plane if an area was experiencing a drought, and that would sometimes help to produce more precipitation. I think they do some of that experimentally now, but nothing on a large scale, because they were getting sued, right? So you would say, hey, that was our rain. Just a quick example of the urban heat island. Excuse me. So this is a recent study. By the way, if there, folks want, I have some references embedded in some of my slides, but if you're looking for the references to anything, just ask me and I'm happy to provide them. I'm kind of forgetting where I got this now. Excuse me. But in New York City, the average heat island, right, is 8.5 degrees warmer than it would be without the urban heat island effect, right? 8.5 degrees, that matters, right? When it's already, and if you're elevating with climate change, it's even worse, right? Oh, I'm saying that this came from the Times on June 22nd. This is another article from the New York Times, right? A ride in a chemical sniffing van, just talking about the production of ozone and some other photochemical pollutants, right? In heat waves, chemicals like formaldehyde, not good stuff, right? And ozone can form more readily in the air, according to researchers driving mobile labs through New York City, right? The bad air has to do with atmospheric chemistry. Professor DiCarlo said while his van navigated the South Bronx, East Harlem, and Midtown with 2 New York Times journalists along for the ride, pollution from burning fossil fuel reacts with heat and sunlight, forming ground-level ozone. I like this quote: higher temperatures turbocharge that process. Right? Oh, here's my little analogy. So you got a 3-story house right here, right? And so back, let's say, early 1900s or something, right? Maybe mid-1800s, right? Before the Industrial Revolution, got going, great guns or whatnot, right? Global temperatures, it's as if we were kind of living on the ground floor, right? With climate change, we're living on the 2nd floor now, right? Change the base level of the temperatures. And now, in certain geographic areas, through things like the urban heat island effect, right, and some other meteorological conditions that I'm going to chat about, probably more tomorrow, we're living in the attic now, right? So we've gone from living, ground level to the attic now because of climate change and some other exacerbating factors. You guys have been here for a whole hour now. How are we doing? Are you over it, or am I getting the high side now? Is probably a good time to maybe wrap up. Okay, I've got a bunch of some of my favorite things to chat about. How meteorology plays a role. I'm going to get into that tomorrow if you haven't been tortured enough. If you're a glutton for punishment and you want to come back tomorrow, we're going to talk about some of the meteorological factors and more particulate sorts of stuff, which I find absolutely truly fascinating. Let's see, a little teaser here. So I did weather on TV many, many moons ago, had a whole lot more hair. In Milwaukee for a while, in Green Bay, Wisconsin for a while, go Packers. And then Concord, New Hampshire. That was a weird gig. Anyway, where was I going with this? Oh, yes, to get you to watch the weathercast, they always have teasers, right? So my teaser is we're going to talk about things like the country breeze. So this is how geography and meteorology exacerbate air pollution. And remember, with a warming globe, we've moved up to that attic area. And then we're going to talk about things like inversions, the lake land breeze, one of my favorite topics. You got that going on here, the lake land breeze, right? Call it sea breeze back in North Carolina, and a whole bunch of other meteorology. So have you come on back for there. I do have a couple of final slides that I'm going to share with you. They're kind of at the end because I didn't know how far I was going to get. I'm always afraid of running out of stuff. So I always you know how that goes, right? Which I never do. I haven't done that in like 35 years. But I know one of these days, my biggest fear, right? So I got to get to the end of my slides. So don't look for a minute, okay, until I tell you when. Don't look, don't look, don't look. Oh, and you get to see me flying, too. Don't quit. Oh, cancel. What's going on here? Technical people. Maybe this will make it move. Okay, good. Uh-oh. What's happening? You're not supposed to be looking. Oh, okay. In just a second, right? So remember, I said we've been doing this for a long time. We're trying to do a better job, right? It's the policymakers, right? It's our politicians globally. We know what needs to be done. It's just they're doing it, and they're finally lifting their head out of the sand. I just like this. I like a little ostrich, right? Before it's too late, right? Cause there's no place like home. So anyway, that's it. Hopefully I'll see some of you tomorrow. I will understand if you want to be out in the weather, beautiful skies tomorrow. So thank you very much. Oh,
I do appreciate you coming.